Good afternoon, viewers. I am Shankar Kumar. I teach the modern European history paper at Department of History in Hindu College, University of Delhi, and I welcome you to this series of interactions on European history in particular, and the topic that we would be talking about today is scientific revolutions, particularly with reference to the personalities associated with this revolution. So, when I say scientific revolution in Europe, think of the second half of 16th century and the entire 17th century Europe and the intellectual climate of this. And we in this particular interaction would not be dwelling much upon the overall intellectual climate of Europe or the historical antecedents on which this particular phenomena, or with reference to which this particular phenomena needs to be understood, because we are limiting this particular discussion of half an hour or so around the personalities associated with the scientific revolution in Europe around 17th century. And when we say personalities, also broadly what you should keep in mind that historians have debated around the issue of scientific revolution in terms of the scientific revolution being a byproduct of a social requirement of the times, or alternatingly, it is also understood by several scholars as personality-led development, which incidentally happened or was clustered in the same century. So, the galaxy of scientists like Galileo, Copernicus, Newton and so forth, Descartes and so forth, they all just happened to be located in the same time context, and it is on account of the extraordinarily high leap of imagination of these people that these attainments could be made, and it should not be understood disproportionately, as argued by some scholars, with reference to the social requirement or the political requirement or the role of bourgeoisie or the role of economy in this. So, it could have happened even even in the absence of these contexts. Now, limiting our discussion today to personalities, let us understand with reference to astronomy, physics, maths. As you can see on your slide, the intellectual successes in these particular subjects provided the kind of intellectual backdrop that was required or that fostered the attainments by individuals in 17th century Europe, and modern historians no more regard medieval age actually as dark age now, because they do acknowledge that significant advancements were made even during the medieval times, and it is by standing on the shoulders of the scholars and the thinkers of medieval times that something very transformative, revolutionary could happen in 17th century Europe. So, entirely it is not understood as have been unfolded in some kind of a vacuum. For example, Nicholas of Cusa way back in the 15th century itself had challenged Aristotle's views, and however, as you can see that he tried to counter Aristotle's viewpoints, but having located some inconsistencies in Aristotle's arguments and postulations, he did not go on to substitute it with a new theory on cosmology, and that was a major, you can say, drawback or limitation of whatever was being attained prior to the scientific revolution in Europe, that is prior to 16th, 17th centuries. So, before that, it is not as if the ancient or classical Greek scholars were given a free kind of terrain over which everyone subscribed to their ideas. That's not true. So, the critical attitude is very much there. People are trying to reassess things, people are trying to see things for themselves, but that element of daring to know is something which was critically missing, and there are stray examples of the ones that I just quoted, like the one of Nicholas of Cusa. Similarly, if you look at the overall climate in the period prior to 16th, 17th century Europe, we discover that even in the universities, what we today study under science was the subject matter, all right, but it was taught as natural philosophy and not as applied science. So, the critical difference that you have to highlight here is the applied part of science. So, it is not as if that scientific inquiries were not being made, but it was not grounded. It was not grounded in the social necessities of people. Rather, it was understood as some kind of an abstract philosophy. So, arguments, very sharp arguments were being made. There were efforts being made to understand several cosmological phenomena around themselves, but that was not with reference to the needs of the time. The grounding of those demands had not happened in a big way, and that is what perhaps happened in 16th century, in 17th century Europe, and that is why what was taught as natural philosophy in a rather abstract way was pulled out of its traditional way of looking at things and was premised on a new, you can say, a new epistemology altogether, which is premised on direct observation, which is sense based, like sensory perceptions. Then to be followed, this observation, sensory perception, to be followed by experimentation under controlled conditions that can be demonstrated, and the cause effect relation can be highlighted between or amongst various variants. And then most importantly, over and above that, we also have the third stage of formulation. So, it had to be formulated as some kind of a natural law, some kind of a natural theory which holds true, which had universal application, even beyond the immediate context in which it was being exhibited or it was being studied. So, it is the applied side of this science which gets accentuated in 16th and 17th century Europe, and that is something that is a critical difference from what was earlier taught as part of natural philosophy, although the subject matter remained the same. So, this is the social use of science. You can see on your slide that I have highlighted here. That is of critical importance. It is this particular dimension that we have to understand, that 16th and 17th centuries Europe is about bringing those scientific inquiries from the abstract domain of philosophy to the real social political needs of the time, grounded in realities. And this is in this regard you can understand the efforts of the Polish scientist, astronomer or cosmologist, you can say Copernicus, and he developed by sheer observation and applying his mind, using mathematics, using geometry, he developed a new calendar which was more accurate in time and date as compared to the existing one, and hence Gregorian calendar, although it is named after the Pope, the existing Pope, but you have to understand that what was happening beneath this is something which is way beyond the conventional wisdom that the church imparted to people at large. So, Gregorian calendar replaced the Julian calendar, which was more you can say traditional and not accurate, and sun and not earth was realized as the center of the universe. Now, today, from 21st century or 20th century perspective, we all know that even sun is not at the center of the universe, and universe is far more big and profound and mystical than we otherwise believe. But the point is that a notion that had been the mainstream notion endorsed by the church as well, and some ancient scholars like Aristotle, etc., who had argued that way, that earth as the center of the universe, etc., those notions are being jettisoned, those notions are being dismantled, and a new kind of premise for creating knowledge, for undertaking knowledge acquisition is being set in the intellectual climate of 16th and 17th century Europe. William Gilbert's postulations about magnetism, and his date is around 1600. Similarly, William Harvey, and this is path breaking, blood circulation, other conceptualizations, ancient conceptualizations, be it Ayurvedic conceptualization here in India or the classical Greek Hippocrates and so forth. They were all at sea so far as understanding this blood circulation is concerned, and it is only in the 16th century that they could get to know in very empirical terms as to what happens as part of supply of blood in human body, how physiology is understood and so forth, and the premise was of course empirical and not model building and trying to hypothesize on the basis of other models that okay, similar kind of process could be happening in human body and so forth. So this is an entirely new methodological premise that we are talking of here. Similarly, John Kepler, and these are some of the important names that we should be talking about with reference to 16th, 17th century phenomena of scientific revolution in Europe. His iconic 3 laws of planetary motion, we have all studied that in our schools. Elliptical orbit of the planets around sun, which earlier was thought otherwise. Similarly, and now again, now the formation of the you can say the circle in an elliptical form or visualizing it required fair degree of geometrical sophistication and so forth, and that were simultaneously happening. So, and all these things require fair degree of abstraction, fair degree of you can say extraordinary leap of imagination. So that was simultaneously happening. I am not saying that the entire thing is reduced to very mechanical exercise of seeing and applying it without much critical assessment. So it required fair degree of leap of imagination as well, and they are fusing the two. But the premise is observation, and it is empirical sensory observation and not going by what the church had said them as truth, as the truth. So they could gain courage to dare to know in a different way, and all these things could not have happened had the movement of Reformation not given a very tight blow to the authority and prestige of the Catholic Church. Similarly, as part of the 3 laws of planetary motion, apart from elliptical orbit, we have planets that Kepler said sweep equal area in a given time interval. This is like if Earth is orbiting in an elliptical path around sun, then when Earth is located far away from sun, and that is the requirement of elliptical orbit. So this variation of distance of Earth and sun will always keep happening if the orbit is elliptical. So when it is far away from sun, then its speed will decrease, and that led Kepler to postulate that despite this speed, so better way to understand or to forecast things is that he could find this pattern that despite the slowness of speed, the area swept by the Earth on account of its orbiting motion would be equal in a given time interval. So, if you take the same time interval, then the area in the form of segment between Earth and Sun would be equal, and this was a big thing, and as you can evidently see, it involves fair degree of geometrical information and so forth. Similarly, his third postulate is that square of time for a planet in orbiting the Sun is directly proportional to the distance from Sun. This is something that I just said to you, and he gives a very distinct number and calculation for this. So, he is not merely talking something which is of general belief, rather he is pinpointedly giving you a calculation by which you can arrive at a unique figure, and this figure will remain unchanged in different circumstances. So, there is some order in nature that is sought to be understood, and that is how in a very precise and defined terms they sought to understand things around themselves. Similarly, another iconic figure that we cannot lose sight of while talking about the personalities during the scientific revolution in 16th 17th century is Galileo, and inventor of telescope. Of course, we all know this, but his more fundamental contribution is that he destroyed Aristotle's concept, which constituted the mainstream of knowledge for more than a millennium. And the best way to understand as to what Galileo was trying to do is to, for example, how Aristotle was trying to understand, say, speed, or for that matter in more precise terms, acceleration. Now, when Galileo is trying to understand acceleration, of course he sees it, he is a witness to things in motion. He is trying to understand as to what speed is, he is trying to understand as to what acceleration is, and what is the vocabulary of his thought process, what is the way in which he seeks to understand understand the speed and acceleration is in terms of the commonly noticed traits like composition of a matter, composition of a particular thing, or quality of a matter, or color or a smell of a matter. For example, intensity of something, like some color is, say, something is of red color, and there is another object which is more red than red color. So, what would you call it? So, you can call it more intense red. So, acceleration was sought to be understood as intensity of speed. Now, what is that intensity of a speed? Can we transform this qualitative understanding of acceleration in terms of or can we transform this qualitative understanding into some quantitative form? Now, that is something that Galileo is doing, and this could not have been possible had he not been aware of the mathematics and geometry that had simultaneously developed in the times that he was living in, and that allowed him to go for that extraordinary leap of imagination and give a particular figure and calculation for this. So, rate of change of speed with respect to whatever factors in a very precise and defined terms, ascribing numbers to all these natural phenomena is something that Galileo did, which Aristotle had been able to visualize. All right, he was observing things, he was trying to understand it, but he was not able to ascribe numbers to it, he was not able to ascribe that formula to it, and that is something that Galileo is doing to transform a qualitative understanding of things into quantitative, and that is extraordinary. So, Galileo premised these understandings on quantifiable units like that of mass, weight, and so forth, and therefore, we have a range of a plethora of discoveries and inventions during the period. You have barometer, you have pendulum clock, you have logarithms by John Napier, which greatly facilitated very complex understanding of qualitative things and the ability of the discoverers and scientists to transform it into numbers. And as you can see that by 17th century, mathematics had provided theoretical basis for statistics, and this statistics went on to become the bedrock so far as social sciences are concerned in terms of its methodology and in terms of several other assertions. Francis Bacon emphasized the empirical basis and inductive method, particular from you move from particular to general, and that is the basis of sciences. Similarly, institutions in 1662 like the one of Royal Society of London were created, which coalesced knowledge from different domains into some kind of an organic whole, and that was important role that they were doing. Similarly, 1666 you have Académie des Sciences in Paris at the instance of Louis XIV and Colbert, who were operating with that mercantilist framework. So, the political undertone is very much visible. René Descartes standing for worthiness of any idea depending on its usefulness. So, what I was saying that it is the bringing abstractions to ground. So, social usefulness, the applied part of it. I think, therefore I am. Now, rationality becomes the new point of departure for any scientific inquiry. Descartes discredited all faulty premises of science. He stressed on mathematics. He talked about the philosophy of dualism, as he said God created only two kinds of reality, mind and matter, and therefore objectivity was very much possible. In 21st century, we can say that it even this is under question now. Mind and matter can be understood as simultaneous and interchanging and so forth. Cartesian followers of Descartes were known as Cartesians. You have Newton, the iconic Newton, who drew on both the Baconian and Cartesian heritages and established optics as empirical branch of physics, and not only understanding it merely as impression of mind. So, infinitesimal calculus, which is another exhibition of theoretical inspiration of Newton, and in effect one can say that Copernicus and Galileo were very effectively combined in Newton's postulation on gravity. So, that sums up some of the iconic figures who punctuated the phenomena of scientific revolution in Europe in the later 16th and 17th centuries. Thank you.